This is Professor Peldon. This is part one of chapter one, section three. So we're going to work with square roots, and then we'll transition to other roots like cube roots and fourth roots and fifth roots after that. What's important to know is first is the vocabulary. A lot of students call this the square root symbol. It is not actually correct. It is the radical symbol because it's used for square roots, cube roots, fourth roots, and so on and so forth. Okay, so the whole thing is a radical expression, right? Just like algebraic expression. And the thing that's inside is a radicand, right? So either you can do it or not. It really comes down to some primes we're going to talk about later. All right. So for any real number a, if you get a square inside, you get the absolute value on the outside, and that works algebraically and numerically. So the question is why is the square root of 9 3? Well, this is 3 squared, right? That's what 9 is. So the answer is 3. Because reality is this little shelf right here is called an index shelf. And for a square root, there's really a 2 there, but they don't tend to put it in the American textbooks. So this operation is the inverse of that operation, which cancels out. So anytime you have a pair or a square of numbers, it leaves the number on the outside or gives you the absolute value. Okay, that's essentially what is going on. And keep in mind that when it comes to a product, if it's the same radical, you can break them apart or you can put them together. And the same is true for a quotient. You can break them apart or put them together, depending on what's easier for the situation to simplify. Okay. All right. So let's try some example problems. All right. So the square root of 1/4. I don't know. I don't know how to do that. Some students might make that as 0.25 and type it into a calculator and whatnot. But using the fact that we can break them apart and put together, I'm going to break them apart. So I get the square root of 1 over the square root of 4. The square root of 1 is 1, and the square root of 4 is 2. So that's good. Oh, that didn't come out very well. Let me try that again. My pen blipped out there. Not sure why. So that gives me 1/2. So that just illustrates sometimes breaking them apart, putting them together is easier. Okay, so again, there's this 2 there on the little shelf, right? So this operation cancels that operation. And you might think to yourself, oh, the answer is -6. No, in fact, the answer is +6. And your question is, why is that? Well, the reality is, in the order of operations here, okay, the innermost parentheses happens first, which gives me 36, right? And then this becomes the square root of 6 squared, which actually cancels and gives you the +6. You have to be careful now with the odds and the evens, okay? Because an even number of something multiplied is positive. Okay, so those ones work out perfectly, meaning everything comes out of the radical, but that's not always true. Let's try 500. So that's 5 times 100, okay, which is 5 times 10 times 10, which is 5 times 2 times 5 times 2 times 5, right? So that is the prime factorization of 500. Let's rearrange it in order. So I'm going to rearrange it into 5, 5, 5, 2, 2. Okay. So I have a couple of pairs of 5s. So I have 5 squared and I have 2 squared. So we know if we break these apart, let me rewrite the middle one here, that 2 of these will cancel. I don't really need to do this much work. I could have stopped a long time ago because I knew right away there was a pair of 5s and a pair of 2s. I could have stopped way back here, but I'm trying to illustrate a point that the square root and the square cancel. These with 5 times 2 square root of 5, right? Because essentially 5 times 5 is 25. We know the square root of 25 is 5. 2 times 2 is 4. We know the square root of 4 is 2. So this gives me 10 root 5. So that is a non-perfect radical. The first two are perfect radicals because everything came out essentially. Okay. All right. And this can be done algebraically also. The same rules still apply. Okay. So let's go down here and try this one here. So if I'm going to break apart 6x, that's going to be 2, 3, and x. And if I'm going to break 3x apart, that's 3 and x. Well, if I look under each of those radicals, there's not a pair of anything. But I can certainly combine these using the product rule. 2 times 3 times x times 3 times x, right? the product rule of radicals. You can look at the top of the page. This is in fact 2 times 3 times 3 times x times x. So I have a pair of x's and I have a pair of 3's. So using that same logic as before, what do I get? I get 3 times x root 2, right? Because this is essentially 3 squared, and this is x squared, right? That's really what it is, which will cancel with the square root, but there's a 2 left over inside. Okay, so the next one is a quotient, and again, I can't really, we just had the 6x over here too, right? There's 6x here, 6x here, nothing we can do with it. But again, we used product rule last time. Let's use quotient rule this time and put them together. So I'm going to get the square root of 48 over 6, and then x3 over x1, right? So you're like, well, how does that make that easier? Well, you can do the numeric and algebraic calculations combined now, right? So you can think about what 48 divided by 6 is. That's 8, correct? So I have the square root of 8, and I have x to the second. Okay, you can break them apart or keep them together. It's up to you. So if I break apart 8, that's 2, 2, 2, and the x's are x and x. And keep in mind as to why this is x squared. This is x3 over x1, which is a quotient rule which you must subtract. So I have a pair of 2's and a pair of x's. A pair of 2's is 4. The square root of 4 is 2. So I have 2x root 2 because there's a singular 2 left over. Okay. All right, so I've used the different radicals, perfect and non-perfect, and I've done quotients and product rules. But the one thing we didn't talk about is adding and subtracting, right? From kindergarten to college, there's only one rule for adding and subtracting. Are they like terms? Well, think of it this way. If I have 2x minus 7x, that's negative 5x. If I have 2 pi minus 7 pi, that's negative 5 pi, right? And you can repeat that process. If I have 2xy minus 7xy, I'm going to get negative 5xy, right? So same thing here. These are actually like terms. So I actually get negative 5 root 5x, right? Because you just add constants whenever it is a like term with a product variable. Oops, I didn't quite make that over. Okay, last two, then I'll have you do some. So we'll break apart the 64. So I'm going to show you a little trick here. So 64 is 8 and 8. And I'm going to have the y broken into y2, y2, and y2. You're like, why do I write 6 y's? Well, I'm trying to do a square root, right? So I need groups of 2, right? I need groups of 2. So there's no sense of writing out all of them because of the fact I need groups of 2. So you just group them by 2. Okay, so the 8s I can break up into 2, 2, 2. So I have 2, 2, 2, and then 2, 2, 2. That's 8. And then y2, y2, and then y2. Okay. So there's a pair of 2's, there's a pair of 2's, there's a pair of 2's, there's a pair of y's, there's a pair of y's, there's a pair of y's. So everything came out, so this is a perfect radical. So this is 2 times 2 times 2 times y times y times y. So my final answer, 2 times 2 times 2 is 8. Y times y times y is y to the third. So that is a perfect radical because everything came out. Okay. And the next one, this will not be perfect. That's because I want to compare and contrast one that's numeric and algebraic where everything comes out, everything does not come out. Okay, so I do a radical here, and I'm going to do 2, 2, 2 for the 8, and then, well, we'll do this two different ways actually. So A2, 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 A2. Fix that line, it's above it. We'll rewrite that afterwards. So that's A8, right? And then B14 is B2, 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 B2. That's 2, 4, 6, 8, 10, 12, 14. You can see how this becomes obnoxiously long, right? So 2, 4, 6, 8, 10, 12, 14. All right. And then we have C5, which is C2, C2, and C1, right? And you can extend that all the way across. So we're going to do this in two different ways. Okay, so first off, pair of 2's. Okay, and then there's 1, 2, 3, 4 A's that are paired. So A4, and then 1, 2, 3, 4, 5, 6, 7 B pairs, and then 1, 2 C pairs, C2. And what's left over is a 2 on the inside and a single C on the inside, right? Because that's C1. Okay, so that's the long way of doing it, which I don't recommend. Okay, what I also recommend is we know this is a 2, correct? So we know this is an 8. So 8 divided by 2 is 4. That's the answer we got. 14 divided by 2 is 7. That's the answer we got. 5 divided by 2 doesn't work perfectly, but that's fine. It goes in twice, and then there's 1 left over. That's the easier way to do it. Because you know it's coming out by factors of 2. It might not go in perfectly, but that's just what's left under the radical. Okay, pause the video. Try the student problem for yourself. Okay, student problems. The square root of 100 over 9. That's a little tough, but we can use our quotient rule and do root 100 over root 9. And the square root of 100 is 10. The square root of 9 is 3. That's a much easier answer, right? Okay, so this is adding and subtracting. There's only one rule for adding and subtracting from kindergarten to college, right? Are they like terms? In fact, these are not like terms. Root 3 and root 12. If they're both root 3 or both root 12, you could add them, but you can't. But I can simplify root 12. So 7 root 3 plus, and I can break down 12. That's 3, 2, 2, right? Because 4 times 3 is 12. So I got a pair of 2's, because we know the square root of 4 is 2, right? So 7 root 3 plus 2 root 3. So these are now actually like terms. So 7 plus 2 is 9 root 3. So whenever you see an addition problem, check for like terms. And if it's not like terms, try to make them like terms by doing your simplification process. Not always possible, but a lot of time is. All right, so 750 is 75 times 10. 75 is 3 times 25. And 10 is 2 times 5. And then 25 is 5 and 5. So all I have here is a pair of 5s, which is 25. We know the square root of 25 is 5. So this is 5 root 3 times 2 times 5, because that's all that's left over. That's inside, right? So this is 5 root 30, right? Make it better than 5 than that. That didn't really work out too well. There we go. So that one's non-perfect. B was non-perfect, but A was perfect, which just means everything came out. Okay, so the next one, D, square root of 5 can't be done, right? Well, you get a decimal, but we don't want decimals. We're not estimating here. We're giving exact answers. Okay, so I'm going to use the product rule to bring these together. So I have 5 times 10 times x3 times x5. Okay, so that gives me 5 times 5 times 2 times x to the 8th. 8, come on, 8. That's not a very good 8. Let's try that again. So I'm using the product rule of exponents to add those together. I'm not going to write out 8x's anymore because we know the shortcut. We're going to do the shortcut now. Okay, so I can take a pair of 5's out, right? So that gives me 5. And then we know this is a second root. So 8 divided by 2 gives me a 4. And what I'm left with inside is a singular 2, with a singular 2 left over inside. So I did the shortcut where I divided the exponent by the index. The index is 2 because it's a square root, right? That's the shortcut trick without writing out 8x's, which is very inefficient and slow. Okay, square root of 2, not going to be possible to give us a nice answer because it's a decimal. So we're going to use the quotient rule in this case. So the square root of 150 over 2, and then x3 over x1. Okay, so half of 150 is 75. And then x3 over x1 is x2. Okay, so this gives me 3 times 25, or 3 times 5 times 5. So I have a pair of 5's and a pair of x's. So that gives me 5x, and then inside is a leftover 3. So that is a non-perfect. Okay, so F is adding and subtracting. Again, adding and subtracting. We did one up here with B, right? But B was numeric. So I also wanted to do one that's algebraic. So these are not like terms because 50x and 32x are clearly not the same. But I can do a little bit of simplification here. We'll see if we can get it to be the same. I don't know if we can. So this is 5 times 5 times 2x, right? Let's see, because 25 times 2 is 50, and then minus 6. And then 32 is 4 times 8, so that's 2 times 2 times 2 times 2 times 2 times x, right? So 4 times 8. Okay, so what do we have that can come out? So the 5s can come out here. So this is 4 times 5 root 2x. Here we have a pair of 2's and a pair of 2's. So minus 6 times 2 times 2 root, and there's a 2x left over. So we have 20 root 2x minus 24 root 2x. Now these are like terms, so I get negative 4 root 2x is our final answer. Okay. We have 2 more down below. G and H. Okay. So G and H, I think one's perfect, one's not, if I'm not mistaken. So this is the square root of 333 x to the 9. So I have one pair that comes out. I get a 3, right? This is square root, so 9 divided by 2 goes in 4 times. That's x to the 4. I'm left with inside a singular 3. And when I divide 9 by 2, I have 1x left over. You don't need to put the first power, but it might be helpful for the sake of a lesson. Okay, so the next one will break down to 32. So 32 is 4 times 8, so 1, 2, 3, 4, 5, right? So that's 4 times 8. And then A9, B16, and C11. I'm going to do the shortcut here again. So I have 2 pairs of 2, so 2 times 2. Inside there's a 2 left over. Okay, so square root 9 divided by 2 is 4. Oh, shoot, I messed up. Sorry. Let me move that over. There we go. 2 left over. So A4, because 9 divided by 2 is 4, and there is 1 left over. 16 divided by 2 is 4. No, 8. What am I saying? I'm thinking the previous answer here. 16 divided by 2 is 8, obviously. Nothing left over. And then 11 divided by 2 is 5. And there is 1 left over. Okay? So to simplify that into 4A4, B8, C5, root 2AC. Okay? Okay. So last is a specialty case for what's called a conjugate. They are irrational conjugates. There are complex conjugates, which we'll go over later. Um, not all of these are conjugates, but the basic idea is if I have a radical in the denominator, if I need to simplify or add something in terms of equations later on or in trigonometry for the ratio, I need to get rid of that radical in the denominator. You don't necessarily for an answer, but if you need to combine it with something else, you're going to have to. So the trick is if it's a singular radical, it's easy. You don't need a conjugate. All I have to do is multiply by root 8 over root 8, which is 1 essentially, and I'll get 12 root 8 over root 8 squared, right? Which gives me 12 root 8 over 8. The 12 and the 8 have a common factor of, what, 4? So that's 3 over 2 times root 8. So that gives me a nice, you can put the root 8 in top too if you want, depending on the context, if it's a ratio or not. Okay, so the problem is when you have multiple terms on the bottom, whether it's 2 terms or 3 terms, or whatever the case may be, you're going to have to use some kind of conjugate to get rid of the radical in the denominator. So in this case, I have 2 terms on the bottom. So I have 3 root 2 minus root 4. So I cannot simply multiply by root 2, because if I don't write this, don't write this, don't write this. If I multiply by root 2, it's going to give me 3 root 2 squared minus 4 root 2 over 8 root 2, which cancels this one, but then we have the problem over here. So that made the problem worse, not better. So if it's something that's a singular radical like the first one, it's easy. Just multiply it by the one ratio of itself over itself. But when it's anything more than one term, you have to use conjugates. So in this case, if it's a difference of a conjugate, you have to use the sum. So this is 3 root 2 plus 4 over 3 root 2 plus 4. Okay. Okay. So put parentheses on it because it's two terms being multiplied by two terms, right? So on the top, I'm going to get, let's see, 8 times 3 is 24 root 2. And then 8 times 4 is 32. Okay, so on the bottom, this is going to give me 9 root 4. This is going to give me 12 root 2. This is going to give me minus 12 root 2. And the last term is going to give me minus 16, which will stick on the end because I can't quite fit it in there. So as a result, I get 24 root 2 plus 32 over 9 times 2, because this is really a 2 here, right? 9 times 2 is 18, minus 16, and you're like, well, why is that? Well, if you look at it closely, that cancels that, which is the point of the conjugate, right? Okay, so I'm going to go back to my pen here. So what I really get here is, so 18 minus 16 is 2. So I really get here is 24. Let's erase the 16 here and actually move this up. That's minus 16. Move that up there just to get this in here. I didn't space this very well. All right, so this is 24 root 2 over 2 and 32 over 2, right? Because 18 minus 16 is 2. So what I really get here is a final answer of 12 root 2 plus, well, half of 30 is 15 plus 1 more is 16, right? All right, so now I've gotten rid of my denominator. All right, pause the video, try the student problem. Okay, so in a singular radical problem, it's easy. Again, you don't need to do this unless you need to like combine terms or solve or something. This is a special case use. This is 6 root 12 over root 12 squared. You don't need to square 12 and get 144. That's not the point, because you get 6 root 12 over 12, right? Because they cancel each other. So I get 1/2 times root 12, or just simply put the root 12 on the top. So you could put like root 12 over 2. That's another way to do it, depending on the context of what you're trying to do. We're just simplifying here. We're not trying to solve anything per se yet. This is the lead up to that. Okay, so we can't do that in a multi-term scenario. We do the conjugate. So the conjugate of 5 plus is 5 minus. Okay, make a better 3 than that. Okay, put parentheses because this is a binomial. So 7 times 5 is 35 minus 7 root 3. Okay, so on the bottom, 5 times 5 is 25. And then 5 times root 3 is minus 5 root 3. And plus 5 root 3. And then root 3 times root 3 is minus root 9. Okay, so that gives me 35 minus 7 root 3 over 25 minus 3, because again, the point of the conjugate is going to cancel, right? So what I really have here is 25 minus root 9, which is 3. So I really have, 22? So I have 35 over 22 minus 7 over 22 root 3. So I've successfully gotten rid of the radical in the denominator in both cases. All right, so that is the end of part 1.